Okay, so we talked about setting goals, and one of the interesting goals, and I just sort of drew this as a sketch, so this is really sort of sketchy. I'm trying. Some people would suggest a useful goal, and I think it's quite a nice goal to try and reach, would be 95% of your maintenance to be condition-directed tasks. I hear people saying to me, "Oh, condition monitoring doesn't work. It's no good. It doesn't work. You find a few bits, but it doesn't really work." So I ask then, well, okay, how much of your maintenance is actually condition directed? 80%? 70%? 50%? 25%? 5%? So how do you expect it to work? If you allow your CMMS system to still plan and overrule your condition data, how do you expect it to work? And I threw up a couple of experiences here. Idea being, 3 different approaches over a 2-year period. Here's my goal. And the first one here is the standard sort of miserable abject failure. We buy the gear, we think it's wonderful, we find a few bits and pieces, then we lose sight, we lose interest, we lose support, we lose our way, and it fizzles out. And then somebody will pick it up again and have another little attempt, and it fizzles out again, and it eventually just disappears. And that's very sad, and that's the equipment that ends up in cupboards. And I'm sure you've all got bits of equipment in cupboards that you'd love to see used again. Then the middle curve is slightly more successful. They've embraced it, had a few hiccups on the way, but they've embraced it. And they've been quite successful with it, a lot more successful than the first group. And they've reached sort of 50-60% of their condition-directed tasks, but now they've plateaued. They've reached a glass ceiling. They just can't get past it. And then there's the third group, that it may take them 2 years, but after a 2-year period of ups and downs and struggles, they actually see the success. They see the goal and achieve the goal, and then it becomes quite easy to maintain the goal. But it's implying and embracing all the technologies, not just ultrasound, but infrared and vibration and oil analysis and motor current analysis and failure mode and effect analysis and a true deep root cause analysis, not this 5 why nonsense, something proper, a proper true deep root cause analysis. These things will help you to do one key word, which is improve. And that's what it's all about. You have to improve and keep on improving. When you sit back and you stop improving, that's the day that you've reached the end. So it's a long process for many people, but it is achievable. I hear horror stories, sad stories. One of my saddest stories was a customer that in a corrugated board packaging company, and I helped them to introduce vibration and ultrasound and thermography, and it was highly successful. But after 5 years, and this is the bit that most of you will recognize, after 5 years there was a management change, and the new manager says, "What are you doing all this for? We don't have problems." "You don't have problems because we're doing this." "No, you don't need that." Just slashed the whole thing. 3 years after that, so now 8 years after launching a program and starting the program, they're back on the phone saying, "We need to do something." "So what do you mean you need to do something?" You had a fantastic program going 2 years ago, well, 8 years ago. It's been cut. So now we have renewed funds to start all over again. What should we do? I said, keep the funds in the back pocket and just do what you were doing before, because that worked fine. Apparently that was the wrong answer. They desperately wanted to be told that there was a new, better way of doing it, which in fact isn't the case. It's all fairly fundamental stuff. So we need to find things that erode productivity. We need to find things that erode profitability. Reliability being an area there, but all of your resources also playing a part. So my air, my steam, my vacuum, any other gases I might have. And I need to look at some of the quick fixes, some of the quick hits, and I need to look at some of the things that will take a little bit longer to do. So, how do I do it? Like everything, small steps. This is a big, long journey. Don't expect that if you say, right, okay, I'm going to leave here on Friday, I'm going to implement this, and by Christmas, I'm going to be God's gift. No. No. It's a process. You need to go through this process. There's a lot to do. You probably have a limited resource, so you need to plan it, and you need to overcome the anxiety that's associated with success, or rather the anxiety associated with failure. Most people are so stressed out about the fact that we've invested 50 grand and we need to see our money coming back, that there's this huge anxiety. We have to very quickly, we have to show. And so then you've got people prematurely calling things, being slightly overzealous, just to try and get the message across. Unfortunately, that anxiety then backfires, because as soon as you have a few false calls, people then say, told you they didn't know what they were doing, told you this was useless. So you have to control that anxiety a little bit. But there are some very easy bits. There are some very easy bits that you can do with ultrasound. And ultrasound is great because all of these things that I'm talking about over the next 3 hours are all ultrasound. So it's the same piece of equipment, maybe a couple of different accessories, some with software, some without, but it's just ultrasound. So the one application, the one set of tools is taking you into all of these different areas. Some of these things are very, very big costs in your business, and they are very easy things to hit and very easy things to put right. Air leaks, vacuum leaks, steam traps, valves, very easy to deal with. And if you remember, the first thing I talked about this morning was how many of you perceive condition-based maintenance to be associated with rotating machinery. And here I show the first 5 easy big hits, not a rotating bit anywhere. Should they be part of a condition-based program? Absolutely yes. Are they related to maintenance? Absolutely yes. In conjunction with your infrared program, you should be using ultrasound on your low voltage, your medium voltage, and your high voltage equipment. There are defects in electrical systems that do not generate heat. If you have a defect that does not generate heat, how useful will your infrared camera be? Won't be useful at all. Best practice these days, if you're going to do inspections on panels, best practice is that before you open the door of an unknown piece of machinery, an unknown panel, you have a listen with ultrasound. This could actually save your life, because you could have an arcing event or some tracking taking place inside there, and you can hear that with ultrasound. So it could actually save your life. There are some aspects which require lesser amounts of preparation as well. So there are things that I can do where I've got some big issues, and yet I can actually achieve these things very easily. But then there are other applications which I require a little bit more preparation to do right. So things like getting a lubrication program working properly, getting my bearing condition checks under control in certain areas, and looking at machine condition. These are things that may need a little bit more preparation to be successful with. So, do I stop doing all the easy things whilst I concentrate on doing my preparation, or do I just go out and be successful? I see so many people get tied up in the preparation. Any of you who've done setups or been associated with setups of vibration databases know exactly what I'm talking about when I start talking about going through the due diligence of finding all the information about the design of a machine. So you're not actually going out and doing anything. You're not actually going out and saving any money. You're just doing research. And whilst that might very well be quite interesting, and yes, of course, it's going to be of value in the future, it doesn't actually save you anything this afternoon. So you need to be doing your due diligence, of course, but keep in mind all these things that you can do straight away. Are all defects trendable? I say no. Does anybody disagree? Speak now or forever hold your peace. Let him speak now. So you agree with me? All defects are not trendable. So why do I need computers for doing all these things? Why do I need routes, surveys for doing all these things, all these defects which are not trendable? There are lots and lots of non-trendable binary defects. Light bulb. I can take as many measurements on that light bulb as I like. I'm unlikely to be very successful at predicting its failure. Another very common one that tends to be a run to failure is toilet paper, but I'm sure that'll get edited out. It's a very common one. It tends to be run to failure, doesn't it? It's failed for most of us over the years. And it's binary. It exists, it doesn't exist. There is a light, there isn't a light. I don't need trending. I don't need history. I can just walk up and say, good, not good. Yeah? So there are lots of defects out there that I can actually just walk up and look at. There are other defects which I need to trend. And there are defects which I can trend just by looking at the overall decibel value very successfully. But then there are also defects that require a little bit more sophistication, where the benefit in finding the problem is by using signal processing and signal analysis. The way to square the circle, of course, is how do you get a piece of equipment in somebody's hands that will do all three? And how do you get a piece of equipment in somebody's hands that will do all three, even with them not knowing? So I can do sophisticated measurement with an unsophisticated person, if I can say unsophisticated person. Lots of non-trendable defects, things that exist or they don't exist. Air leaks, steam leaks, vacuum leaks. Tightness testing, very, very big. Inspections on things like heat exchangers, corona arcing tracking problems, testing steam traps. Even some basic rotating machinery analysis can be just simply looked at in a binary way. It's there, it's not there. So there's lots of areas that I can just hand somebody a piece of equipment with no history, with no extra data and years of preparation, just training. Just training. I can hand them a piece of equipment and say, you can now, with your training, identify these problems. Today. So the true simplicity of ultrasound is that it will deal with all these categories. It will allow you to simplify. And I don't need gigabytes, terabytes of data. I've been doing vibration for a long time now. The first computer and software I had was in 1988. It was DOS-based software in 1988. And if I think of it between 1988 and 2011, bless you, how many terabytes of data I have. Don't push it. And it's one of those things that when you talk to people who have mature vibration systems with many gigabytes of data and all the time and effort involved in collecting that data, what percentage of that data is machinery with a problem? Is it 5%? 10%? Maybe 15%? Probably won't be more than that. 75 to 85% of the data that you've collected over all those years, that I know that I've collected after all those years, is no fault found, green light, okay, normal, whatever you want to call it. But I've spent as much time taking that data as I have taking the data on something that has a problem. Does that make sense? To me, it doesn't. And this is an area where ultrasound plays a big role. So I have the same hardware dealing with all these problems. So when I'm talking about return on investment, this is very easy. And another contentious point. Many defects can be diagnosed by ear. Ooh, you can't do that. You have to have a database. You have to have science. You have to have digital signal processing. You have to have alarms. I love that one. You have to have alarms. Yes? People who are fixated on alarms. The alarm level is 10. Okay, the alarm level is 10, fine. It's 9.995. Is it an alarm? No, because it's not 10. Okay, thank you. Thank you. Fixated by alarms. I remember a chat in one of the reliability web chats a couple of years ago. We were talking about identifying a problem of a leak on a hydraulic cylinder. And somebody wrote in, how did you define it as a problem? Did the manufacturer give you data to tell you what was the bad condition? No. Good. So much can be diagnosed by ear. So much. Very simply. It does not need a huge amount of sophistication. You can just go out and do it. Does that lower the credibility of this technology? Does it raise the credibility of this technology? Or does it actually have nothing to do with credibility? It's just a very useful thing. How many of us would still grab a screwdriver and do this? Huh? Yes? The comment from the floor, it's the only thing I have. Look at this as a 21st century digital screwdriver with a memory. That's all it is. Does the same job. I can listen. I can listen to all sorts of things that are going on. Trendable defects. Probably the most well-known trendable defect is lubrication. Very simple for us to trend using decibels. And A true decibel scale has a unit associated with it. A decibel scale is a relative measurement. In the case of the equipment that I use, we refer to a voltage. So everything is referred back to a reference value of 1 microvolt. So that's why we have this unit of dB microvolt. That's not a U, it's a micro. There is a basic misunderstanding of decibels. Most people don't understand. When I teach level 1 and level 2 ultrasound courses, it's definitely the thing that I spend the most time trying to explain is logarithms and decibels. I'm not going to do that now, but suffice to say, a few golden rules about dBs. Never, 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 ever, never, ever divide or multiply dBs. You only ever add them and subtract them. And simple things to keep in mind is that 6 dB is double, 20 dB is times 10. So the increase from 30 to 36 dB is not 20%, it's double. The increase from 40 to 46 is not 15%, because we never, never, never divide decibels. It's not. It's 6 dB, and 6 dB is double. So when you're doing trending, you have to get used to thinking with numbers in a different way, because these are logarithmic numbers, not linear numbers. And it's the hardest thing to get used to. But you have to get used to it, because you can let things slip if you don't. Lots of areas for taking dynamic data. And I can use dynamic data in many, many areas for finding problems. And I'll show you some of those this morning as well. But things like arcing, tracking, steam traps, gearbox analysis, all these things, vibration applications, listening to valves, analysis on recips, all sorts of areas like that. Being able to capture and process a dynamic ultrasound signal gives you a very, very powerful diagnostic tool. When you are setting up a program, you do need to think about due diligence. Where are my items? We could have a rider to that question, which is, where are my drawings? This normally highlights 1 or 2 problems, doesn't it? What are they called? What are my assets called? No, not what do you call them, what does everybody else call them? Because again, I see many, many cases where one department calls something, they number it 1, 2, 3, and another department numbers it 1, 2, 3. Or you think about an oven in a food factory, and some people count from the in-feed, and some people count from the door. And so what it's called is completely different. There's a fault on number 4 motor, and somebody pulls out the wrong motor. No, not that number 4, that number 4. That's not number 4, that's number 2. Oh, sorry. Fault on number 2 motor then. How do my assets change with operations? What's running, what's not running, what's running hard, what's running light? These things change. How does this affect my measurement system? Do I need to go out on a specific day, or do I need to go out as part of a specific process to try and catch particular bits of equipment? I need some organization there. We talk about measurement intervals and measurement frequencies. How often do I need to go? Can I use alarms? What sort of alarms can I use? What will the alarms mean? What will I do when I have an alarm? Things to plan ahead. If I'm thinking about setting up a leak detection program, there are things I need to consider in terms of the pressures, sizes of orifices, viscosities of the gases that I'm using, how good my instrument is at detecting, how sensitive it is, what measurement frequency am I going to use, distances, how far away can I get, how near can I get, do I have the skill as an inspector to deal with that? Don't send somebody out that hasn't been trained. They will inevitably make mistakes. When you're dealing with your air leak system, your compressed air system, do you have any layouts? Do you have any drawings? Do you have any drawings that were made within the last 5 years? Because it seems to be one of those things that changes quite a lot. Do you understand direction? Do you understand direction of flow and supply and demand? Again, what do I call things? Where are the points of my highest consumption? These are all very important things to consider. So there's all sorts of areas that I want to think about in terms of how am I going to use my system. And again, training is a very, very important part, because with training you can explain to people the right way of doing something and the best way of doing something. So how to use the right sensor to get the best results, to be the most sensitive system, and so on. How am I going to document my leaks? How am I going to mark them up? Can I see them? Do I have to have additional protective material with me just to make sure that it's easy? Am I going to follow a path? Am I going to follow the line of the pipe work? Am I just going to go into a room and have a quick listen? How am I going to communicate and coordinate with plant supervisors so that they know I'm here, why I'm here, and they can say, oh, don't come now, we're just about to do this and this and this. Or come tomorrow because we use more pressure tomorrow, we've got the system backed off today. So things like that become very, very important. Following the system round, planning my execution. A very interesting place to start is probably in the compressor house itself. It's amazing how many leaks you find in the compressor house. You know, your precious air never even made it to the factory to leak. It just didn't get out of the compressor house. And don't forget to take into account things like dryers and filters. Lots of dryer and filter companies use this technology, so keep that in mind. Vacuum leaks is another big area. Huge area. Anybody worried about vacuum leaks? Big problem? Can't wander around with steam. You can't wander around with your smoke system as easily for finding vacuum leaks, and squirting it with Snoop doesn't work terribly well either, does it? Ultrasound works really, really well for finding vacuum leaks. Really, really well. Two things to keep in mind. Firstly, you probably might need to think about fixing your air leaks first, because a vacuum leak is, generally speaking, quieter than an air leak. So I've been in several places where they've had vacuum leaks, and it's been very hard to find the vacuum leaks because of the number of air leaks. So we've really had to struggle to shield the area to allow us to actually pick up the vacuum leaks. But it's very easy to do. The second point, because it's the sound is travelling into the pipe. It's not going out. So a vacuum leak is always that bit quieter than an air leak. There is a very, very interesting case study, and I'll show you some pictures of that later, on finding vacuum leaks. Actually, really interesting one, this, because this was actually on insulated piping and insulated ducting. So it was a contact measurement. It wasn't an airborne measurement. It was measurement on the outside, on the cladding, of some insulated ducting with fantastic results. Steam systems, be very careful. Steam is deadly. It really is deadly. So certainly, the first point there is from my own personal opinion. I would like to be as far away as possible. Yes. I still see people wandering around with large poles and rags tied on the end trying to find steam leaks. Very, very dangerous. Tagging can be very dangerous. You know, because you can't get close enough to the vacuum leak, to the steam leak to tag it. Finding and fixing leaks is also unlikely. So photography is probably your only best way of dealing with that. And steam is very, very noisy. So steam leaks are very easy to detect. Very easy to detect. Once you're on the steam side, then the next thing we go into is steam traps. Again, a very simple test with ultrasound. Normally, the best combination is actually the combination of ultrasound and temperature. And if you happen to have the ability to do both at the same time, then that is an added advantage. Don't send a boy out to do a man's job. Definitely the case when it comes to inspecting steam systems. It's very, very important that your inspector knows the steam system. You have a cold section. Is it cold because it's not in operation, or is it cold because you have a blocked steam trap? You need an inspector that knows the system to be able to tell the difference. In other words, to know what is running versus what should be running. You need to think about promoting in the steam system an efficient heat system. This is what it's about. We're trying to increase the efficiency of your heating system. I've been in situations where there have been so many leaking so many problems with steam traps, so much air, so much condensate in the system that they've not been able to achieve a certain temperature. And without being able to achieve this particular temperature in a food industry a case, they were unable to cook the product properly. Or the cooking time was extended. The transit time through the oven had to be slowed down because they couldn't reach the temperature. In a pharmaceutical plant, they couldn't achieve temperature inside an autoclave with their steam system to actually trigger a chemical process. So sometimes having an inefficient steam system can actually be a big, big cost. But when you've got leaks there, you've got problems with costs associated with chemicals, extra chemicals needed for treating the water, extra costs of fuel, extra costs of all sorts of materials and labor. Ultrasound can also help you extend the life of the very expensive assets that you've got in your steam system, like your boilers and your condensers and the heat exchanging systems and the steam recovery systems and all the rest of it. So testing for tightness, testing for leakage in those areas, very, very important to be done. And ultrasound is definitely the best tool to be doing that with. When we talk about steam trap inspections, there are 3 ways in which we can do that. We can rely solely on doing it by ear, which is the way it's been done for years. You know, don't get me wrong, temperature and ultrasound is still the #1 way of testing steam traps. But the definition of good and bad tends to be something that's passed on from almost father to son. For me, the great interest these days with steam trap testing is how to make that objective. How to, for example, capture a time signal of a dynamic signal of a steam trap and say this is a good one, this is a bad one, because we can compare it with another one. So I think personally the combination of the 2 methods is my preferred way of working. Listening, and when I hear something that I'm not too sure about, then having the ability to dynamically record it and then process that signal. And it's really, really simple to do. You know, a quick, hopefully this will work. Okay, no it won't. Worked yesterday. Isn't that just typical? Thank you. That's a working trap. Sometimes it can be quite And then you've got all sorts of horror stories. Very easy to hear the difference between a good one and a bad one. Very, very easy. And we use temperature as well to measure the difference between the upstream and downstream side. Again, very, very useful to combine the two technologies. If I use temperature, I can understand the thermodynamic behavior of the steam trap. But if I use ultrasound, I can actually listen to what's going on inside. So the combination of the two gives me all the answers. Very simple and easy to do. I just need to use a contact probe and put my contact probe on the steam trap, and there we are. We can listen to it. The next logical extension of that is valve inspection. Anybody got any critical valves? Stupid question. You've got process valves that are critical. You've got hydraulic systems as well. And you've got some critical valves in your hydraulic systems too. So how do you inspect those? Do you inspect those? Or are they all on run to failure? Or are they all on intrusive inspection? We have to wait for a shutdown and we strip the valve out and we have a look. Well, with my ultrasound system, I can look at 3 different aspects of my valve condition. I can look at leakage. I can look to see if my valve is passing. I can inspect a valve to see if it's blocked. And a third very big killer of valves around the world is cavitation. Cavitation kills so many valves, especially automated systems. When you have automated systems where a valve is opening and closing and there's nobody around, nobody knows it's screaming its head off due to cavitation. And it just fails prematurely. And nobody's taking care of it. So the amount of money that I can save in terms of valve inspection could be vast, absolutely huge. And I can, again, treat my valve inspection program just like anything else in terms of setting up a database of my valves, setting up a system of going through and taking the readings. This is something that sometimes might even be better trendable, because then I've also got some evidence that I can show to insurance companies and so forth to say this valve is working normally and has been checked and inspected every couple of months for the last 5 years. And now it's starting to show signs of failure. So that can be a very, very useful thing to do. Again, very simple. We're just going to be using a contact sensor and listening upstream of the trap, downstream of the trap, and trap, valve. And so upstream of the valve, downstream of the valve. And if it's a large enough valve, big one, we might also take a reading on the valve stem itself. Very simple. Very simple. I can bash through and take care of all my critical valves on site. Because right now you have nothing. Yes. You've never heard of cavitation in a valve. It's very common. And if you ever suffer from sleepless nights, I have a wonderful, approximately 80-page PDF document which goes through all the physics of it. And if you can get past page 8, you're doing much better than I am. But, or that I did, rather. But it took me several days to get through that document. It is a huge problem. It is a very common problem in valves. A simple example, I was in a roof void in a pharmaceutical plant last year, and the valves in their steam system were all controlled by computer, and I was probably 200-300 feet away from a valve, and as soon as this valve went past 40%, it made so much noise from cavitation that 300 feet away I could still hear it ultrasonically. It was that bad. And as soon as it went back down below 40%, it stopped. It's very common. Surprisingly common. And all I'm going to do, as you see here, is listen above and below. I don't need to disassemble. Saves a large amount of time. And just like everything else, I can now generate a hit list of areas where I want to do some additional work. Electrical applications, high voltage switchgear, problems like corona and tracking, big problems on high voltage switchgear, but they don't generate heat. So you will not find corona and you will not find tracking with an infrared camera. You can see corona with an ultraviolet camera for sure, but the self-same piece of equipment that you're using for all your other airborne ultrasound applications, you can take outside and you can listen to your high voltage switchgear with. And I'm going to give you some examples of people who are using it for finding arcing inside. There was a document that was produced many, many years ago here in the States on extending life of transformers and in that document there's a whole section on using ultrasound, and it covers all manner of things. It's not just things like arcing and tracking, but if it's an oil-filled transformer, I can use ultrasound to listen to flow, so I know the oil is circulating. But I can also use it as a loose parts monitor. I can listen to the flow and I can hear if there's any rust or anything or any loose bolts or something circulating around inside the oil. I speak sometimes, as you know, with mechanical people and electricians, the two dysfunctional groups. And let's take an example of an oil-filled transformer. An oil-filled transformer will have a pump. Mechanics won't go near that because the electricians won't let them because it's a transformer. But the electricians won't touch it because it's a pump. So I said, well, who looks after your oil pump? Nobody. And that makes sense to you? No. So you have to watch out for these things that fall through. And again, this is a very nice case where I can combine my two alternative methods. I can either think of it in terms of just having a listen, having a trend, or using diagnosis. So we'll spend a little bit of time looking at and listening to signals that have been captured using ultrasound. But I can extend that beyond my transformers to switchgear and relays and bushings and poles and bus bars and capacitors and all manner of things. Again, it's the same piece of equipment. I may need a parabolic dish so that I can be far enough away to be safe, but that's the only extra accessory that I might be required to use for that kind of application. So it's the same hardware, just switch the sensor to give me what I want. And there are people now who are doing things like on-condition cleaning of bushings. Instead of having any power station people here, you'll have planned outages on your big transformers, right? And you're trying to extend those outages from 12 to 24 to 36 months maybe. Ultrasound gives you the opportunity of doing on-condition cleaning. There are guys who are combining ultrasound and infrared and dry ice cleaning to actually go to a transformer that's running live, say, that bushing there needs cleaning. And then using dry ice live, clean that one bushing. And then go back and check and say, yes, it's okay now. So when we start thinking about find it, fix it, check it, we've actually found a problem, dealt with the problem, proved the problem has gone away, and it's been completely non-intrusive. I think that's a success. Lubrication. So many things that you can do in terms of lubrication, in terms of switching from time-based to switching over to condition-based lubrication. We can work then in a way where we're gathering data. Not only are we identifying the bearings that need lubrication, but we're also, at the same time, identifying any other problems that there might be on those bearings. So now I'm doing my basic condition monitoring and my lubrication at the same time with the same guy. How good is that? No. Back. The guy who's doing the grease route is out taking data, not out greasing. The guy who's doing the grease route is out taking data, and based upon the results of that data, only greasing those bearings that need to be greased. Yes? So he's collecting all the data, which means that you don't need to go out and have somebody else collecting the data. And if you set that up in terms of a find and fix method for doing the lubrication, he's coming to a bearing, identifying that that bearing needs lubrication, performing an on-condition lubrication using his ultrasound system so that he knows he's walking away from that bearing and it's now okay, and moving on to the next one.